So today we're going to be learning about radicals and also learning about how to simplify them. So to start off, we're going to start off with what the idea of a root is. So we are really used to taking square roots. So we know if 5 squared equals 25, that means 5 is the square root of 25, or 5 equals the square root of 25. We might be less familiar with the other one. So 5 cubed equals 125 means 5 is the cube root of 125, or 5 equals the cube root of 125. Then 5 to the 4th equals 625 means 5 is the 4th root of 625, or 5 is the 4th root of 625. So if 5 to the 5th equals 3,125, 5 is the 5th root of 3,125, or 5 is equal to the 5th root of 3,125. So basically it means what multiplies by itself 5 times to get 3,125. So we're going to define this for nth root. So what that means is if we instead don't use 2, 3, 4, 5, we use n. So if a to the n equals b, then a is the nth root of b. So that means a is equal to the nth root, we kind of tuck it in that little corner, of b. And we're going to learn what that little corner means in a minute. So if n is odd, so odd exponents like 3, 5, 7, 9, then there's only going to be one real nth root of b, which is nth root of b. If n is even, like 2, 4, 6, or 8, then there are 2 real nth roots of b, plus or minus, so don't forget plus or minus the nth root of b. We've seen that with something like x squared equals 9, and I tell you when you take the square root of both sides, don't forget plus or minus, right? That's that common mistake that we talked about a few units ago. So if you take the square root of both sides, you have to say x is equal to plus or minus the square root of 9, which means x equals 3 or negative 3. So that happens for even exponents. But if we have an odd exponent, like 3, then there's only going to be one real root. So we're going to see that in a little bit. So the first thing we want to get through is some notation and some words that we use to describe these. So the radical sign, this sign right here, indicates a root. The number under the radical, so this a right here, is called the radicand. And to be honest, we don't use that word too many times, but the one that we do use is this one right here. So the index gives the degree of the root. So this n right here is the index. And so we're going to be using index a lot. We'll use radicand a little bit, but index is the one we kind of want to focus on. So now we have a property that's the nth root of nth powers. So what does that even mean? So let's say we're trying to find the nth root of a to the n. So you can almost expect that something's going to cancel out. So it in fact does. So this is equal to, we've got two options. So we're going to use this little doodad. It's equal to a if n is odd. And it's equal to the absolute value of a if n is even. So let's try that out. Let's say we start with this first example. Now notice there's no index here. If there's no index written right here, you can assume this is really like a 2. So this is really like an index of 2. So if we have the square root of 16, x to the 8th, let's rewrite this using the index of 2. So how can I write 16 so that the exponent is 2? let's think, what number squared is 16? Well, 4 squared is 16. How can I rewrite x to the 8th so that the exponent is 2? If we think back to our exponent rules, what number when I multiply in is going to give me 8? It would be a 4. So now I have some number squared times some number squared, and I'm taking the square root. So what I can say, the square root of 4 squared, if I look at my property, is just 4. The square root of x to the 4th squared is just x to the 4th. So this is how this property comes into play. So in general, for an index of 2, you might want to write this down. The square root of x squared, or some number squared, is just x. So this is a nice, really important one to remember that you use a lot more frequently almost than the other ones. Let's try an index of 3 now. So in this second example, I'm going to use what I know about exponent rules. So I have my 3 tucked away. To rewrite a to the 6th, so it's a raised to some power to the 3rd, because I want my index to match that number. So what number would I have to plug in so that I get back 6? It would be a 2, because 2 times 3 is 6. Now I'm going to rewrite b to the 9th. So it's b to the something cubed. That goes right there is a 3, because 3 times 3 is 9. So now that I have my index matching up with my exponent, I can use this property. So if I cube a cube, or cube root a cube, it cancels it out. So this becomes a squared, just cancels out everything else, times b cubed. So this is a nice little shortcut to help us. Last up, let's try with an index of 4. So if I have an index of 4, I'm taking the 4th root. I want to rewrite this so that things cancel out. So I want x to something to the 4th and y to something to the 4th so that they, oops, I didn't want to cancel there, so that these cancel out. Well, I need to get back to x to the 8th. So 4 times what is 8? 2. And here I need to get back to y to the 12th, so 4 times what is 12? 3. Now that I'm taking the 4th root of something to the 4th power, it cancels out. So it just becomes what's on the inside. X squared times y cubed. Everything else cancels out. Now that's a really nice shortcut if you're good at rewriting things. But we can also simplify radicals the same way we simplified square roots. Remember when we used a factor tree and then we looked for things to go on dates that kind of paired up together and got to leave? We're going to do the same thing here, but with different pairs. So for an index of 2, we're going to end up looking for pairs of 2. So let's try to rewrite this. 64 is 8 times 8, which is 2 times 4, 2 times 4. And I circle my primes. Now, p to the 4th is really p times p times p times p. You don't necessarily have to do a factor tree here for that. But remember, if it's to the 4th, it's multiplying 4 times. So now let's rewrite what we have. This becomes the square root, 1, 2, 3, 4, 5, 6. So 2, 2, 2, 2, 2, 2, times p times p times p times p. Now let's look for things that get to go on a date and leave the square root or leave the house. So this gets to leave as a 2. This gets to leave as a 2. Remember, it leaves as kind of 1. So 2, 2, 2. And now p and p. So this is what we end up with, which is really 2 cubed times p squared. Or if you want to multiply out, since 2 cubed is pretty small, we can multiply that out to be 8p squared. Now, in this next one, this is going to look a little bit different from what we are used to. So now we have an index of 3. If we're looking for an index of 3, we are looking for pairs of 3 that get to go on a date and leave the house. So this is where it gets a little bit different. So now let's see. We're going to set up our factor tree the same way. 20 times 16. Those are two numbers that multiply to 320. 20 is 4 times 5. 16 is 4 times 4. 5 is a prime number, so I'll circle it. Now I get 2 times 2, 2, 2, 2, 2. And so let's rewrite what we have now. And remember, a to the 5th is just multiplying by a 5 times. So we're looking for the cube root. 2 times 2 times 2 times 2 times 2 times 2 times 5. And now 5 a's. Scooch that one in there. All right. Now, since we have a cube root or an index of 3, we're looking for pairs of 3. Here's a pair of 3 that gets to leave the house as 1. Here's a pair of 3 that gets to leave the house as 1. And here's a pair of 3 that gets to leave the house as 1. So we are left with 5 times a times a. Our last step now is to simplify. So 2 times 2 is 4 times a. The square root of 5, and a times a is a squared. So there is our final answer. And oops, I forgot. Remember, our index still has to be a 3 right here. All right, we're going to try a few more. So in this next one, I'm looking for index of 3, so I'm looking for pairs of 3. So 256 is like 64 times 4. So 2 times 2. 64 is 8 times 8, which is 2 times 4, which is 2 times 2. And now let's rewrite what we have. So now we have cube root of 2 times 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 2. Did I miss any? Okay. Times x 6 times. Let's look for pairs of 3 now, because we have an index of 3. These get to leave the house as 1. These get to leave the house as 1. Those 2 get left over. These get to leave the house as 1. And these get to leave the house as 1. And then on the inside, we're left with those 2 times 2. Now we simplify. 2 times 2 is 4. X times x is x squared. And we're left with the cube root of 4. All right, let's try another. Again, we are working with an index of 3, so we're looking for pairs of 3. So I set my factor tree up the same way. 32 times 10 gives me 320, which is 2 times 5. And 32 is 16 times 2, which is 4 times 4. Which is 2 times 2 times 2 times 2. Let's see what we have left over. Now, notice we have x's and y's, so we're going to have to figure out how to deal with those. So we're looking for cube root. 1, 2, 3, 4, 5, 6. So we've got 6 of these 2's. We've got a 5. We've got 3 x's. And we have 8 y's. Now let's look for pairs of 3 because we have an index of 3. There's a pair of 3, or a triplet. Here's another triplet. Here's another triplet. Here's another triplet. Here's another triplet. And on the inside we are left with, we've got a 5 left over and we have 2 y's left over. Now your last step is to simplify. 2 times 2 is 4. x doesn't have anything to multiply with, and y times y is y squared. And now we're left with the cube root, 5 times y, which is y squared. And that is as simplified as we can get. Let's try 2 more. Now we have the 4th root. So in this case, for 4th root, we're looking for pairs of 4. So we are going to multiply out. Let's see what multiplies to 648. Well, I know it's divisible by 2. If I divide it by 2 on my calculator, I get 324. 324 is 81 times 4, which is 2 times 2. 81 I know is 9 times 9, which is 3 times 3, 3 times 3. So let's gather it all up. This time we're looking for a group of 4 to go out and leave the house together. So 3 times 3 times 3 times 3 times 2 times 2 times 2. Now we've got 5 x's and 2 y's. So we end up with, now we're looking for pairs of 4 this time. So these get to leave the house as 1, and these get to leave the house as 1, and I actually don't have any more sets of 4. So I'm left with 2 times 2 times 2, which is 8. I'm left with an x, and I'm left with 2 y's, which is y squared. I can actually shorten that a little bit. And there's my final answer. For our last one, again, we have an index of 4. So we're looking for groups of 4. So 243, that's divisible by 3. And if I divide by 3, I get 81. 81 is 9 times 9, which is 3 times 3, 3 times 3. So let's rewrite what we have. And remember, this time we were looking for pairs of 4. So 1, 2, 3, 4, 5. And now we've got x, y's, and z's. So 1, 2, 3, 4 times y times z times z times z. Let's look for our groups of 4. We've got a group here, just 3. We've got a group here, which leaves the house as 1. And that's all we can do. So on the inside, we are left with 3 times y times z times z times z, which is z cubed.